Welcome back, grade 12s. Now let us continue with our review, and in this case, it will be of question 8, which is a cubic function, and that will need some good use of calculus and calculus knowledge. In most cases, you just need to know how to derive, and you need to know the special features of a cubic function. Okay, so now we're given this function here, which is negative x cubed plus 6x squared minus 9x plus 4 is equal to, and this side here, we're just given the factorized form of the same thing. So this is in terms of its x-intercepts right there. So we know that anytime we have x-intercepts, in most cases, we don't have the value of x as negative. So we can maybe just write it out as equal to, we can factor out this negative from this equation here. And we have negative outside, and we have x minus 1 all squared. And here we have x minus 4 like that. Yes. So this looks a bit cleaned up because it matches the energy of this one, where you know that the value of A is negative. So here it's lost. That information is lost when it's written like this, that the value of A is negative, right? So when you have it in this form here, then you can quickly see that the value of A is negative. Yeah. So it gives you the idea and the shape of the function, and you can easily solve for x-intercepts when they look in this manner. Okay. So now let's go on and solve the questions. 8.1 says, determine the coordinates of the turning points of f. So in this case, we know that anytime we're dealing with the turning points of the cubic function, we'd have to use the first derivative. Now, why do we use the first derivative? It's because at the turning points, the gradient is equal to 0. So this simplifies the equation once you derive it, and you can set it to 0, so mean that there's no y value that you're actually looking at, okay? So let's derive. So f of x prime will be equal to, this will be negative 3x squared plus 12x negative 9 like that, okay? So now we know that at the turning points, the gradient is 0, so we can quickly set this to 0. 0 is equals to negative 3x squared plus 12x negative 9. So to simplify the entire thing, we can divide by negative 3 both sides. So we still have 0 that side, and this side we have a much more simplified equation. So we are going to have positive x squared right there, negative 4x, and we're going to end up with a positive 3 like that. So this is easier to see what are the values of x that would give us a 0 right there. So 0 is equals to, and we can quickly factorize that. So x here, x there, and we have negative 1 and negative 3 like that. Okay. So what does this tell us? It tells us that in this case, the turning points happen at x equals to negative 1. Sorry, x equals to positive 1 and x equals to positive 3. So have we known this information? Yes, we could have. Now, I want you to look at the function here given. Do you see here, it says we have, these are the factors, right? But here we have a repeating bracket of the factors. So this means that this function, this cubic function, has a turning point as well as one of the x-intercepts happening at the same place, okay? So it means that x equals to 1, which is a x minus 1 is a factor up here. X equals to 1, that function changes shape or changes direction from increasing to decreasing or decreasing to increasing, depending on the shape in this case. So it means that this is a turning point as well as an x-intercept, okay? So here we know that the values of x would be x equals to 1 or x equals to positive 3. So they were looking for the turning points. They're looking for the turning points up here. So how are we going to report the turning points here? We know that x is 1, and we need to evaluate the original function when f is 1. And the other one will be x is 3, and we need to evaluate the original function when x is 3 on f, okay? So this turns out to be, well, this is 1 and 0. We've seen it from up there. And when you punch in your calculator right here to find out that value, so this will be 3 and when I punched my calculator, I found that this gives me a 4 like that. So remember that you would have to find out what this information is, isn't it? So meaning that you have to punch it into your calculator and you have to substitute into the original, right? Not into this, okay? So we have negative into 3 cubed right there. And what was the original? We had, let me just check up there. We had plus 6 x squared minus 9. Yes. So this will be plus 6 into 3. And I think this is negative 9. Negative 9. Let's have it. So this is negative 9 into positive 3. And we had a plus 4. So this gave me a value of 4. Okay. Let's go on. So it means that the turning points happen at these points here. Okay. So we're happy about that piece of information. Now let us go on to 8.2. In 8.2, there's a draw a sketch of F, clearly label the intercepts with the axis and any turning points. Okay. So from this piece of information here, we know that the y-intercept would be at positive form, okay? And we know that the shape should be one that is negative. And we can just give a little description on how we can remember that shape produced by this. And we know that one x-intercept, which will also be a turning point, will be at positive 1. And the other one will happen at positive 4, like that. Okay. So we know that with functions, with cubic functions, we have two shapes in general that we can deal with. We have this one, or you could have this one right here. Okay. So now which one is which? Which one produces is positive and which one is negative? Now you have to look at the value of A. In this case, if A is positive, then you'd end up with this function right here. And if A is negative, then you'd have to end up with this function right here. So now how would I remember it? Looking at the value of A, it's positive, right? So I look at the general shape at the end that I will have. And this is a smile. So I take it as a smile, right? So if A is positive, I will end up happy with a smile, okay? Yes, it all ends in smiles. Now, if A is negative less than 0, then I look at the shape right there and I say, well, it's a frown, so it ends in tears. So that's how you could definitely remember these shapes. So just keep that in mind. Okay. So it means that since our value of A is negative, this is the shape that you and I are going to have. So let us have our sketch here. So I'll just draw the function. So x and y like that. Okay. So then I could just have it something like this and something. Okay. So now I know that this point here is going to be 4 and 0. How do I know that? Let's go up here. Let's go up here. They gave us this piece of information, and we know that this is in terms of the x-intercept. In this case, the x-intercept also acts as a turning point, this guy there. Okay, and we know that this is 1 and 0. We have solved for it before, and we know that this guy right here must be 3 and 4 because that was the other turning point, and you want to have them level like that. Okay, you want to have them level. So because this is going to be 0 and 4. And this would be your function f like that. And that would be a nice sketch in my books. So if you would write something of that nature, I'll definitely give you full marks. Okay, let us go on to 8.3. What are they looking for? They're saying use the graph to determine the values of k for which this function is equal to k will have 3 real and unequal roots. Okay. So now I will have 2 approaches to this. Okay. We're going to have 2 approaches to this. So they're saying we have x cubed, right, plus 6x squared minus 9x plus 4 equals to some value of k like that. Now, if I transpose the value of k to the other side, what I'm going to end up with is plus 6x squared minus 9x plus 4. Okay, let me just use a different color right here. And let me just say I'm going to have negative k, which is going to be equal to 0. And now I must end up with how many? 3 unequal real roots. Unequal real roots. So this to me says that k would be some, if I move k to the other side, just the way I did here, it means that k is some shift of some sort, such that my function of f will have 3 unequal roots. So right now, this function has 3 roots, but then 2 of them are equal. Because when I solve the entire thing here, I would say x equals to 1 or x equals to 1 and x equal to 4. So in this case, as it stands, I have x equals to 1 or x equals to 1 or x equal to 4, where these 2 here are repeating roots. So now I want to move this graph of ours such that I will have 3 real roots. So here in this case, as it stands, I could shift the graph down, right? If I shift it by 1 unit downwards, then I know that it will cut in 3 different places. But then I could do that to a certain extent, isn't it? Because there will be some point where this right here, this turning point is down here. So let me just have that in a different pen, and let's just have that sketch. Okay. So probably something like that. Okay. So I could move this function down, but then there's going to be a limit to by how much I could move it down up until I do not observe this anymore. Okay. And those will be the values of k that I could move it down by. And if I decided to move it upwards, also again, I will have a limit to how much I can raise the function by. Okay. So now, how are we going to find this value like that? Okay. So now what I wanted to check is that the highest peak here in terms of y values, that's 4, right? And the lowest that I have here is 0. Okay. So now it means that if I move it by any number that is between these 2 values, then this graph, what will happen to it? It will have 3 real and unequal roots for that matter. Now remember that my k here started out as a positive number. Me shifting it to this side should not influence the outcome or the value here. Hopefully that makes sense. Okay, so it means that the values of k that we can choose should be between what? 0 and 4. Because when I take this side, then it will become a minus of that value. So like it could be -1. So that would be a shift downwards. But then we started out with the original question where we were given a positive value of k. So the final answer here should look like this, that k must be any number that is between 0 and 4. Now, in this case, I'm not going to include 0, neither am I going to include 4, because when I move it 4 units downwards, then I'll be violating this unequal part, okay? Because these 2 would be equal roots right there. Okay, hopefully I have made sense there. Okay, then another way in which you could observe this is to treat k, let let K be some function, or let K be some function, right? Maybe we could say h of x equals to K, right? Okay. Now, when they say that when these two functions meet, f of x equals to h of x, we want it such that f of x, no, h of x cuts h of x or f of x at 3 different places, okay? So let me use a green horizontal line. So I could place it up here. If it passes at y equals to 4, right? If I have a function called h of x, and it passes right here at y equals to 4, then I know that it cuts the graph into 3 parts, but then it would have repeating roots here. So we don't want that. So it means that I must pick a value of k, which is going to be less than 4, right? And then if I choose that, maybe let's say 3, then I let it to be 3. Do you see that it cuts here, right there, and right there? And these would be 3 real and unequal roots. Values of x for which the function cuts the graph. And there will also be a limit, right, by how much I can take this value of k by. So the limit here would be when I choose h of x to be equals to 0, then it would have a repeating root there and that root there. So it means that the values of k for which I can allow for h of x would be between 4 and 0. And I wouldn't have to, I should not allow k to be greater than 4, isn't it? And I should not allow k to be less than 0, effectively giving us the same answer down here. It's just a different ways of analyzing the same question. Okay, let's go on to 8.4. Hopefully 8.3 was clear to everyone. Okay. Right. Now, 8.4, they're saying that the line g of x equals to ax plus b. Now, my good people, I don't want you to be confused. Usually, when you have a straight line like that, it's given by mx plus c. But the letters mean the same thing. This a represents the gradient because the coefficient of x, and this b represents the constant, which is the y-intercept. Okay? So they mean the same thing, even though they're using different letters in this case. Now they're saying that this line is a tangent of f at the point of inflection of f. Determine the equation of G. Okay, so since they're talking about the point of inflection, we know that we must refer to the second derivative, because that's how we're going to get information about P of I, which is the point of inflection. Right, so let us go on right there. So I'm just going to start with the first derivative because I know that I've derived that in a previous equation or in a previous question, which was 8.1. So I'm just going to take the same information. I'm not going to derive it again, but I'm going to write it for that question. Okay, so which is negative 3x squared plus 12x negative 9. So negative 3x squared plus 12x negative 9. And what I really want to get to is the second derivative right there, okay? Because this is the function, or this is the derivative that has information about the point of inflection. So this will be negative 6x plus 12. So these two, if I would make side notes on them here, I know that the first derivative gives me information, gives info about gradient. So now, if I need anything related to gradient or where the function is increasing, decreasing, I know that I could rely on this guy because it gives me where the function is increasing, decreasing by the means of gradient along the function. And now, right here, the second derivative gives me information about the point of inflection. And now what's so important about this is that this is where the graph changes concavity. okay, changes concavity. So maybe instead of writing what it does, I could just say second derivative. I did not wipe this part out. So I could just say second derivative gives info about concavity, where the graph definitely changes its behavior on where it's facing. Could be concave up, could be concave down, okay? So this is where we are going to get this information. And we know that where it changes that concavity, that's what we call the point of inflection. Right. Excellent stuff. Right. So now they said that the tangent g of x is attached to this function at that point. So now we need to find this point. But we know that the second derivative only gives us information about the x value of the turning of the point of inflection. So now we know that inflection at the point, or we know that, yes, we know that concavity, rather, at the point of inflection is neutral. The function is neither concave up nor concave down. So neutral is represented by 0 in this case, and we can solve for that value there, the x value of p of I. So if I take 6 to the other side, we see that our value fx must give us a positive 2 like that. Okay, so now we've found this value. We've found the x value, right, where the tangent is going to be attached to. So we can find the entire point of contact by substituting this value of x into the original function. So when x is 2, this is the same thing as saying minus into 2 minus 1 all squared. And here we had 2 minus 4 like that. I believe that it's 2 minus 4. Yeah. Looking at I'm using this right here. That's the one I'm using. Instead of using this long one right there, I'm just going to use this one that since it was provided to us. But it's also safer to just use what you have been given on the question paper, even though these two things are the same, okay? They're referring to the same thing. Okay, so what do we have here? 2 minus 1. 1 squared, still 1. 1 negative, negative 1. And then right here, we have 2 minus 4, which is going to give us how much? Negative 2 multiplied by negative. This will give us a positive 2. So it means that the point of contact, the full coordinate of the point of contact will be 2 and 2 like that. Okay, so now we have the point of contact, the full point of contact where this function is going to be passing. So this is the point of inflection. This is the full coordinate of the point of inflection. So now another thing that we can use here or have to find is we can find what is the gradient when the x value is 2 of the function, isn't it? Because that will be the same gradient that will be carried by the tangent at that point. Okay, so we know that anytime we're looking for information regarding the gradient, we are going to consult the first derivative. So what is the gradient here? So I'm just going to call it m. M is equals to, now, what is the gradient when x is 2? So I have negative 3, 2x squared right there. And I believe this is positive 2 into that. And the value that I'm getting here is 3. So I'm finding that the gradient is positive 3. I believe that here I should have a negative 9. Yes, because it had 3 values. Yes. So this is the value that I'm getting for the gradient right there. Okay. So now I could use the information, the point of contact and the gradient to find the full information about g of x. So now g of x is equals to ax plus b. So I know that the value of a is going to be 3. We've just calculated that. And we might just need the value of b like that. Okay, so the formula that I'm going to use here is y is equals to m into x minus 1 plus y1. Now I'm taking this formula from this formula here. Usually this is how it's given, okay? But I know that I just want to solve for y, where y stands for g of x, okay? So this is 3 into x minus, what is that value there? We had 2 plus, what was the y value there? We had 2 again, okay? So now when I distribute this information, I will say I will have 3x for this guy here. Now here I will have 3 times negative 2, which is going to give us negative 6. Now, negative 6 plus 2, that will end up with a negative 4 like that. So that is the entire equation of g of x. Nice and easy. I loved it. I definitely loved that one. Okay. So let us check the last question there. What are they saying to us? So probably if you just want to have a mini sketch, it could pass through that point right there, isn't it? I'm just guessing it could pass through that point. Let's just make sure that it just touches that one value, okay? If I had a nicer sketch, maybe this would be our function g of x. That would be the tangent at that point. But please make sure that it passes through just once, because it's a tangent, right? Okay. So what was the question for 8.5? Let's look at it. Now they say calculate the value of theta, the acute angle. So anytime that they're talking about the acute angle, we know that it's less than 90 degrees. Formed between G and the x-axis in the first quadrant. Excellent. So let us look at this piece of information. So we know that this is in the first quadrant here. So that's the one that we're going to take. Now, our angles are measured anti-clockwise. So we know that it's from the positive x-axis to the line itself. And that gives us, it means that theta in this case is the angle of inclination, right? So we know that the formula for that is given by, I think I should just write 8.5, yes. So m is equals to tan theta like that. I believe that's why it's just 2 marks. And when you're looking for the angle right here, given that you have the gradient, it would just be the inverse function of that equals to theta. So now in this case, we have 3 equals to that. And when you punch in your calculator, you are going to get a value of 71.57 degrees like that. Thank you for joining in, and I'll see you on the next one. Cheers.